Okay, we're talking about the composition of the atmosphere, which means what it's made of. So if something's composed of something, it's made of that thing. So the composition of the atmosphere is what the atoms are made of that are around us. So if I grab 100 little molecules of air, okay, I grabbed one here, all randomly, would they all be the same?
No.
What elements would I be grabbing though?
Oxygen, nitrogen, and then some random.
Which one would be the most?
Nitrogen.
Nitrogen, huh? So you picked that up from the homework? Time for a pie chart. Okay. So, what's the biggest piece of the pie? What, at what percentage, remember?
78.
Yes.
70-something.
78% of it is nitrogen. Okay, so if I grab 100 molecules of air, we have Andy count them up. How many of them are nitrogen?
78.
78. What's the next one? What's the next percentage? Go ahead. Yeah. At what percentage? 21. What's 78 plus 21?
99.
99. We're already at 99%. So if we grabbed 100 random molecules, 78 of them would be nitrogen, 21 would be oxygen, and only one of them would be something else. You know what that something else would most likely be? I'm curious what you're going to say with your hands up. Andy?
Carbon dioxide.
That's a good guess, but that's not it.
I got another guess.
What's your guess?
Carbon monoxide.
No? Argon. Yes. At. Surprisingly, right? Right here are the trace gases. Now those trace gases, if there's only 1% total, 0.93% is argon. What is argon? Anyone know what it's used for? It does sound familiar. Argon is used in light bulbs. So a light bulb, it lights up, but it doesn't start on fire or anything. That's because there's argon around it. Argon is a noble gas. Remember noble gases?
No.
Noble gases don't react to anything, like helium, argon, krypton, all this other stuff that just does its own thing. Neon, yeah, it doesn't react with anything. The electron shells are so stable that they just don't bond. They stay gas and they stay like that. Yeah.
So it's not like neon science? Or...
Well, that's why neon in the neon science doesn't turn into neon oxide or silicon neon with the glass. It stays neon even though the electricity is making it glow the way it is. Yeah, so neon is a noble gas, and when you pass the electricity through, it glows. Trace gases, 93% of that is argon. 0.04% is carbon dioxide. That carbon dioxide, what does this add up to? Of that remaining 1%, almost all of it is 0.97% is argon and carbon dioxide. So of that very, very, very trace, there's stuff, and I'm not going to give you a total list. Okay? Yes, krypton is on the board, but you know. Radon would go on here.
Ozone.
CFCs. CFCs are a very low percentage now, but I want you to have it in here so when we talk about the ozone layer next, you'll remember it. CFCs, ozone, methane. These are all greenhouse gases. Well, greenhouse gas, greenhouse gas, greenhouse gas, greenhouse gas. But more on that later. Those are our trace gases. When you take a breath in, is that mostly useful to you or mostly useless? It's mostly nitrogen going in. Most lots of waste. All right, so when you breathe it in, what are you trying to get? When you breathe out, what are you breathing out?
Carbon.
Air.
So if you breathe in 21% oxygen, you're actually breathing out about 20.5% oxygen. You don't use all the oxygen you breathe in. That's why like mouth to mouth was effective. You're breathing out most of that oxygen anyway. You're not using all of it. Anyway, those are our trace gases. Here's a different way of showing it. Argon of this little tiny slice, we end up with mostly carbon dioxide and little slices of other things. So it's mostly nitrogen, mostly oxygen, just a little bit. Now if I pulled 1 million air molecules out of the air, and Andy counted them up, stacked them, piled them, sorted them for us, in 20 years it'd be done. How many of what would he have? He'd have 780,000 nitrogen particles. He'd have 210,000 oxygen molecules, but he would only have about 400 carbon dioxide molecules. So it'd be a big pile of nitrogen, 780,000 nitrogen, but only 400 carbon dioxide. There's not very much there, is it? So here's a question. If we tape the door shut, tape the vents, tape the windows, no air in, no air out, what would happen to us eventually? We would, why? We would use up all the oxygen, pass out, die. Why doesn't that happen to the Earth as a whole? I mean, we're using oxygen, there's no new air coming in, no whatever else. Why are we not just dying using all our oxygen up, Eva? What's the key word we're going for here? Starts with a P.
Photosynthesis.
Thank you for all the gusto in that answer. Photosynthesis. What does photo mean? Do you really not know? Photo is the prefix that means light. So a photograph is a
Light picture.
yeah, it's a picture made of light. Anyway, photosynthesis. What goes in? What do plants need to survive? Carbon dioxide and light and water. Yeah, so you take carbon dioxide, you take 6 of them, 6 carbon dioxide, you take 6 waters, and what else do plants need?
Sunlight.
And energy. This is called a chemical formula. So you take these things, what do we get out? We get it, man. Yes, we get glucose. Well, how many people knew that?
Oh, I did. You learned that last year.
D.
Thank you.
D.
You get glucose out, and what else?
Oxygen.
O2. Oxygen. This oxygen is a waste product. It's a byproduct. It's exactly. Okay. So why is it doing this if oxygen is a waste? What's it really trying to get?
Sugar.
Sugar. Okay. Do plants use sugar to grow and survive? Yeah. They use 90% of it. So if a plant does this 100 times, it's only going to end up keeping 10 glucose molecules. It'll use 90 up in just growing, surviving, reproducing, all sorts of stuff. So plants use up most of what they make. On the flip side, what is it that we do? We don't do photosynthesis. We do something else. What's that process called?
Breathing.
Breathing. Start with the fancy science word starts with an R.
Hyperventilation.
Respiration.
Wow.
On the flip side is respiration. Respiration. What goes in? What do we need in? O2. And what else do we need? What else do we need to do respiration? What else do we need to survive? Lungs. That's what gets it into our blood. You had a big bowl of it this morning.
Energy.
Glucose.
Further, man.
For the win.
Okay. Okay. Now we don't just need glucose, but this is the most basic way we can show this. We take oxygen and we take a sugar molecule. We take fat, which is just lots of sugar molecules. Well, no, it's not. We take oxygen. We take a sugar molecule. We burn the sugar molecule. What do we get, Danny? What are we getting from our food in the morning? Energy. But what else? What else are we giving off then as a waste product? Waste product, Rachel?
Carbon dioxide.
What else?
What else?
Besides, yes, carbon dioxide is correct, but what else besides that? Breathe into your hand. What are you feeling?
Heat. No.
Air.
Tell you. You're feeling heat, and that's the energy. But your hand gets all like, so what are you giving off? H2O. This water, the water you're exhaling isn't just the water you drink. Maybe a little bit of it is, but most of that water is water you made in your body as you did respiration. That food that you made, or the food that you ate, plus the oxygen go into making energy, carbon dioxide, and water. So you're exhaling your breakfast. You're exhaling your dinner from last night. Right now, that water, that was that tuna casserole you guys had. Well, I forgot the sixes. Yes, 6 carbon dioxide, 6 H2O. Excuse me. Now, what do you notice about this chemical equation? What do you notice about this one? Take a look.
It's in reverse.
We have 6 carbon dioxide, 6 water and energy over here, making glucose and oxygen. Over here we have glucose and oxygen, making 6 carbon dioxide, 6 water, and 6
It's
energy.
the opposite.
It's a cycle. It's this, this is the exact same as this. It's a process. They depend on each other. And this depends on this. Now, do we have any other way of storing energy besides plants like this? What other food source do you have that's not plants?
Bacon.
Where do they get their food source? So what's their food source?
Plants.
Okay, somebody do something very energetic. Okay, you're all flailing your arms. Where did the energy come from flailing your arms? Where did the plant get its energy from?
Sun.
The sun. Where did I get the energy to toss this pen up in the air?
Sun.
The sun. Yeah, all of my energy, everything that I've used to do this class has come from the sun.
Interesting.
Thanks, son.
It kind of blows your mind. Back to this. Is this oxygen and this carbon dioxide, are they connected in any way?
Yeah.
Yeah. So we're using oxygen up. We're decreasing this, but plants are decreasing this. And there's a balance there. Okay? Here's the writing part of the notes. So I tried to avoid it. I guess not too hard. Uh-oh. Here it is. Okay. Hold on a second. This is the oxygen, carbon dioxide balance. Part of the notes. Okay. Here it is. Until humans began burning fossil fuels for energy, oxygen and carbon dioxide levels were in a natural balance. But since then, carbon dioxide levels have been rising. So I'll give you a second. Carbon dioxide levels have been rising. When did humans start using fossil fuels?
Since the
1890s. No.
Since they burned coal.
Okay, so people have been burning coal for a very long time. This should say since humans began burning fossil fuels in large amounts, which was basically the Industrial Revolution. Remember that?
Yeah.
Like
1920s.
1800s.
Yeah, the late 1750s with factories and machines, and people started burning stuff like crazy.
Is there a word between fields and energy?
And the trees
Sorry, what?
and the plants can't
Okay.
absorb
Well, I
that
couldn't see it.
CO2.
I'm sorry.
And the plants can't absorb that much CO2.
Well, what else are we doing? What are we doing to the plants? Big rainforests. Yeah, a lot of rainforests have been disappearing too. So we're not going to belabor the point here, but here is a graph. Here's a graph. Back in 1960, gentlemen, CO2 concentration was 310 parts per million. So, back in 1960, we pick a million random atoms out of the air. Andy sorts them for us. How many are CO2? 310.
310.
Today, this graph isn't complete. Now it's up above 400. And we're not going to belabor the point, but I just want you to know humans are affecting this level. Okay? We haven't talked about the greenhouse effect yet. We're not going to go into that today or tomorrow this week. But you just need to know that carbon dioxide concentrations have been going up. Why again?
We're burning fossil fuels.
We're burning all those plants and animals, all that energy that was stored long ago, and the earth has been kind of shielding us from it. And so now we're releasing it all at once. Yes, Andy.
But isn't that good for the plants? Don't the plants get more carbon dioxide?
The plants get a small boost, but we're cutting down more than we're boosting them.
Alright.
Good question. Final thoughts? CO2 and respiration, or excuse me, photosynthesis and respiration. You will be expected to know this link, kind of. Here's what's generally happening with plants and how this is working. Here's how respiration is the flip side of that, and how they're doing that. So, I mean, that's it for the notes.